The field line plotting routine. Don't worry about these lines, but we're going to do this, what we call a loop, until xq equals 999, and we put the conditions where we cut off the loop down here, which basically occurs when the x and or the y coordinate gets too big for the screen, or for the equipotentials when the y coordinate becomes positive. Okay? We find the field strength and direction for the field due to Q1. Okay, now x1 and y1 are the coordinates of Q1. X and y are the coordinates of the point at which we're plotting the field line. Okay? X, well, from Q1 to the point xy, the x displacement is just x1 minus x. And I said that wrong. From xy to the field line, here's our x displacement and here's our y displacement. Call that R1x and R1y. To find the distance back between our field point and our charge at Q1, we just use the Pythagorean theorem on R1x and R1y. We take the square root of the sum of the squares and get our distance from the charge. So it's all very simple. We're just using our Pythagorean theorem and a little bit of trigonometry. Sine 1 stands for the sine of the angle made by the vector from x1, y1 to xy. In other words, from our charge to our field point. So there's the sine of the angle of the vector. So if we got a charge here and a field point down here, we have a vector like this. This gives us the sine, this gives us the cosine of that angle. And actually, I think that's a negative of the sine and a negative of the cosine, but don't want to worry too much about that right now. I'm trying to give you the flavor of this, and there are a few specifics that I've left out of this program, or at least the version that you're seeing. If you want, email me. I'll email you back a version of the program if you have an editor. Okay. So the field strength is going to be what? Just Q1 over R1 squared. R1 is a distance of the field point xy from the charge. R1 squared, of course, is the square of the distance. And you divide that into Q1, and that's the field strength. I didn't put a K in front of this. I'm essentially, for the purposes of the program, letting K equal 1 because the program is just interested in directions. It doesn't really care if this is times 9 times 10 to the 9th or not. So the field strength here isn't ever going to really appear on the screen. It's there to give the program the relative field strength between the strength from charge 1 and the strength from charge 2. Now, we do the same thing for the charge Q2. We get the x and the y components of the vector from the charge, actually in this case from the field point to the charge. We use the Pythagorean theorem to find the distance of the field point from the charge. We find the sine and the cosine just by taking the x and the y components of the vector divided by the vector length. And we get the field strength for charge Q2. And we call that field strength 2. Then we come down here and say, okay, the x component of the field at the point xy is field strength 1 times the cosine of angle 1 and field strength 2 times the cosine of angle 2, because angle 1 and angle 2 are the angles to the two charges for which the field strengths were calculated, so that the cosines of those angles give us the x components of the angles of the field strengths. Okay, so this is the field strength in the x direction for the field from charge 1. This is the strength in the x direction from charge 2. We do the same thing with the y. We multiply the field strength from each charge by the sine of the angle of the field at that point. And from that we use a Pythagorean theorem to get the field strength, just taking the two components, x and y components of the field strength, and adding them up. Then the sine and the cosine now are the sine and cosine of the angle of the actual field. We take the y component of the field by the magnitude, and that gives us the sine. We divide the x component by the magnitude. It gives us the cosine of the angle of the field. So at this point we know what the direction of the field is. And this is what we're really after. Because when we plot field lines, okay, here we are at x, y. We're going to move a little distance in the direction of the field. And the sine and the cosine tell us what direction to move. So now, depending on what our choice is, in case 1 where we're plotting field lines, we're going to move from the point x, y, we're going to move negative 0.1 unit from the point x, y. So that we move negative 0.1 times the cosine, or negative 0.1 times the sine, and we multiply by q over the absolute value of q. Q over the absolute value of q is going to be positive if the charge that we're looking at is positive, negative if the charge we're looking at is negative. It's either going to be positive 1 or negative 1. So this allows us to always move away from the charge, and that's a subtlety you don't have to worry too much about. The whole point is we just move 0.1 unit in the direction defined by the cosine and the sine of the angle from wherever we are. So that if the vector is in this direction, the cosine and the sine will lead us to move in this direction, parallel to the field. If we have choice 2, this is the choice 2 part now, we don't move negative 0.1 times the sine and negative 0.1 times the cosine as we did before. We move positive 1 times the sine and negative 1 times the cosine. The reason for that being that we want to move in the negative reciprocal direction. If we move in this direction, then our motion will have be the negative reciprocal. Well, the slope of our motion, the slope of our line segment will be the negative reciprocal of what it would have been if we were doing field lines. This takes the equipotentials in the direction perpendicular to the field lines, just using the idea of a negative reciprocal slope being perpendicular to a line with a given slope. So at a point x, y, instead of moving in the direction of the field as defined by the sine and the cosine, we flip the sign, we go the negative sign, and we go in the perpendicular direction. Then after having moved to the new point, or after having defined the new point x, y, depending on whether we're in choice 1 or choice 2 plotting field lines or equipotentials, it doesn't matter. We've got the coordinates of x, y now. All the computer does is draws a line from wherever it is to the new point x, y. Now where it is the old x, y. It's sitting there at the old x, y, and it just moves to the new x, y. In the direction of the field, if it's plotting field lines, perpendicular to the direction of the field if it's plotting equipotentials.